Good morning, everybody. I'm really glad you're still on board, even for the last day. And don't worry, so the lecture today will be much less technical than yesterday. So what I'm going to do, this was the roadmap I gave you yesterday, and I realized we actually more or less covered half, so that's nice. I will give you a very brief reminder in a few slides of what you should have retained from yesterday. And then you will see the more, let's say, to some extent relaxed part, because then I want to show you on some examples what we can really expect from the combined GW plus DMFT scheme. And I will discuss what is existing, what is not existing, what should be existing, and what we can hope for and what we can't hope for. Okay, so yesterday we convinced ourselves that you can write the free energy of a solid in terms of a functional of two variables, the Green's function and the screen-Coulomb interaction, which on the way we also reinterpreted as the propagator of a Hubbard-Satonovich field of some bosonic degrees of freedom used to decouple the Coulomb interactions. So you can think of this as describing, for example, density fluctuations in your system. Then we have argued that this free energy functional has a trivial mean field part, which is more or less Hartree, and the interesting part, hiding all the many body physics, which we don't know exactly, and for which we have to do approximations. This latter psi functional part here has the properties that its derivatives with respect to its two variables g and w gives you the self-energy for the one particle and the two particle quantities. So the self-energy of the polarization, I call it self-energy for the two particle quantities because the equations were quite parallel. Okay, then we were asking ourselves what the DMFT point of view on these functionals would be, and concluded that in this representability point of view, you can actually view DMFT as a way to construct an auxiliary system, and this time some effective atom that generates the local parts of the quantities you want. And we were discussing that in order to generate not only the local Green's function, but also the local Coulomb interaction, we needed to extend that auxiliary system, and instead of just having an atom coupled to a self-consistent path, as in usual DMFT, we needed to have this atom itself carry dynamical interactions, and this was a second auxiliary quantity, second on top of the usual dynamical mean field, the Weiss field, that then we have to determine in a self-consistent fashion. Okay, that's what I just said. And then we discussed how to go ahead if we want to combine GW and this extended dynamical mean field point of view. And we did that on the functional level by postulating that our approximation to the psi functional is a combination of a local part stemming from DMFT and a non-local part stemming from GW. We were discussing that this requires the definition of a notion of locality. If I'm on a lattice model, that is trivial. I know what is on-site and what is not on-site. But if I'm in a solid, I have to define atomic-like orbitals, Wannier functions, NMTOs, whatever you want, but something which has a reference to some side index so that I can decide if things live on the same side or not. In that way, so this notion of locality is really different from the notion of locality that the electronic structure people are used to. So in electronic structure theory, you call a potential local if it depends just on one variable, little r, right? But here, the notion of locality is really the notion of on-site in an atomic site picture. And then we discussed that GW non-local is nicely defined by just saying that we take the GW functional, GWG, and subtract its local part. Okay, so that was essentially the hard work, except for one further step, namely the derivation from this functional of the set of GW plus DMFT equations. And these I have re-summarized here for you. So that's what you did on the blackboard yesterday. You did a great job, right? You worked out all this stuff here. So you were working that you have an impurity model defined by the dynamical mean field, as in usual DMFT, and defined now also by the frequency-dependent Hubbard interaction here, the auxiliary interaction that I have to determine in my self-consistent loop. This impurity model with 1 and 2 particle Baire propagators, so to say, I solve it by calculating both the Green's function in the usual way, just as an expectation value of the time-ordered C dagger here, with the action resulting from these two quantities. And I also need to calculate the screened interaction, which we discussed as being related to the charge-charge correlation function. So that charge-charge correlation function tells me about the density fluctuation in the system, and that gives me the screening. So the Baire interaction of the impurity model, the U here, is screened by this chi to give the W of the impurity model. We also discussed that this is a purely local picture. We are looking purely at local screening processes, and I will come to that, back to that point later. Once we have these two quantities, you have the self-energies, namely you have the usual Dyson equation for the one particle quantity, but you also have a Dyson-like equation for the two particle quantities, Baire interaction -1, screened interaction -1, and the difference is precisely the polarization that has screened these. And then we discussed that the essential step in GW plus DMFT is not just to go ahead with the sigma impurity and P impurity here, but to supplement these quantities by non-local parts stemming from GW. And this combination really was a consequence of the postulate for the functional that I just was saying, local plus non-local part. So with this non-local and local self-energies and polarization, I go into the self-consistency condition. The first line, again, you know already. That's the usual DMFT self-consistency condition. And the second one tells you the same for the screening. So what are we requiring here? We are requiring that the Baire Coulomb interaction, and please note that this is really the Fourier transform of 1 over r minus r prime, the Coulomb interaction in the continuum, screened by the P, which has both local and non-local quantities, gives you a W whose local part, this is why I sum here, should be the thing that now I use in the two-particle Dyson equation, that is just the inverted thing of this, to update the U, to update the dynamical interaction. Okay, so now here these equations update me both the Weiss field, the dynamical mean field, the way you know, and the auxiliary interaction to be put back in my impurity model. And then you iterate. So these equations look horrible if you look at them at first sight, right? When I flash this slide, so in most workshops I don't dare, but when I dig it out, people go back. But actually the nice thing is you know half of this cycle already because you had studied DMFT before. So if you compare, the first line in each box of what I've shown you before is precisely the DMFT loop. Solve the impurity model just defined by this, get the self-energy, plug the self-energy in the self-consistency equation, and with that local Green's function, you improve your Weiss field and you iterate, right? So what we have done, and now I will reconstruct you the equations here so that you see that, we have added everywhere a second line, and that's what we call extended DMFT. So that is entirely parallel to what you have seen before, except that everywhere you have the second line for the two particle quantities, with the translation, really, that Baire propagator is U, real physical quantity is W, the physical quantity is W, and the associated two particle self-energy is P. If you have this vocabulary somehow, then the loop is nothing else than your one particle DMFT loop. But then I'm still missing this box here because this was just DMFT with the two particle quantities, and this box is precisely where GW comes in, namely where I supplement the local parts with the non-local parts stemming from GW. Okay, that's as far as we got yesterday. Are there questions at this point? Everybody more or less likes these equations now. Okay, so then, yes, then solve them. Okay, and I will come back to the question how to solve them, not very in detail, but first I want to give you a motivation why to solve them. So let me tell you a little bit what this gives. And I will do that not in the ab-initio 1 over r minus r prime with all the Coulomb interaction and all the orbital complications part, but I will do that on the really most simple model first, and then increase the complexity slowly. You had seen the Hubbard model. You had discussed that, okay, fermions hopping on this lattice here, and when they meet, they interact with this Hubbard U. That was really sorry. That was really the minimal description of the interplay of localization and delocalization for correlated materials. And you probably also know that you can extend that model to include nearest neighbor interactions. So that was my Hubbard model, and now I have added a term here where the sum runs over nearest neighbor, so where I punish also interactions if they live on neighboring lattice sites. Very simple model defined by that Hamiltonian. I'm not confined to do everything ab initio, so I can do my GW plus DMFT loop for that Hamiltonian. And the nice thing is that in that case it's so simple that you can actually play around a lot and try things. And that's what a very bright PhD student here, who did his master with Philip and then came for a PhD back to Paris, actually he was in Paris before, did. And I should also give credit to Ping Sun and Gabi Kotliar, who did a similar study in 2004 already, very early on. But at that time, they had relatively, well, limited Monte Carlo, so they could barely see things on the Matsubara axis, whereas now with these new techniques here, developed by Philip, we are able to really do analytical continuations, to do with full self-consistency everywhere, to look at the quantities that we want to study. Okay, first let me show you the phase diagram that we get for this extended Hubbard model. Well, if there's no V, so here on this axis you have U and V, and just look at one set of lines, for example the green lines here. If there's no V, then you just have the mod transition going from the metallic Fermi-liquid phase to the mod insulator. That's the usual thing you have even studied yourself yesterday, I think, with IPT, right? However, if I switch on intersite interaction, what will happen? Well, at some point, the interaction between two neighboring site fermions becomes strong, and so strong that people do not want to have neighbors. They prefer sitting on a site to pay a U and to avoid paying the nearest neighbor interactions. So that means you go into a charge-ordered phase where you will generate, for example, on this square lattice here, a kind of checkerboard phase where you alternate occupied and empty sets. So if the nearest neighbor repulsion is strong, that is clearly favored, and that's what you see here. So now, having an idea about the phase diagram, let's, yes? Yes, so I didn't want to go into these details, but indeed there is a question on where this value should be, and this is why we did actually studies looking at different decouplings here. Yeah, of course. So this is on the square lattice, plain vanilla. So, okay, I think there's more to discuss, but okay, we can do it offline. Yeah, but it depends on which decoupling you do. So it's subtle. So, okay, let's discuss that offline. Let me first continue the general course here. So let me look, because the thing I really want to look at is now spectral functions. We are making a whole story about GW not being able to be self-consistent and not to be able of getting Hubbard bands and so on. So we have to check these things now. And what we plotted here is the spectral function nicely in the metallic phase, but as you see, in the correlated metal, where you have a renormalized quasi-particle resonance of the kind that you have seen several times already this week, and then this coexists with the Hubbard bands, with the features of electron removal and addition in a localized picture, so atomic-like features here. And who can interpret the evolution with V for me? So if you look at these curves, without V, the dark line here is this thing, right? And then we increase V, and this decreases here. This becomes slightly stronger. What does that mean? Exactly. So that means the effective view actually decreases when I increase V. And that's actually not so surprising, because it just means that the nearest neighbor interaction tends to screen the effective interaction. And now when I talk about effective interaction, I'm talking about this curly auxiliary quantity that enters in my impurity model, which is not an adjustable parameter anymore, but is calculated on the fly. So I will have now, let me make sure that the notations are clear, actually, because this could be a little bit confusing. So the model is such that you realize U and V are now the bare interactions. And when I talk about effective U, I talk about the curly U, which is the local part where this thing is screened by effects stemming from that. Okay? And you're absolutely right. So increasing V screens, increasing V reduces the effective static or the effective interaction of my impurity model. And that's what you see here. Yes? Oh, it's half filling, so it's always at the same thing. Yeah, yeah. Oh, the peak height. Yes, the peak height. The peak height is a subtle question. In principle, if you were at 0 temperature, it would remain pinned. However, we had finite temperature here, so that means when you are more or less strongly correlated, you also are more or less close to the coherence regime, so the peak position will vary somewhat. So at 0 temperature, it would strictly be pinned, but here you have actually small effects also on the height. Yeah. No, single side DMFT, but GW plus DMFT. Okay, I'll come back to that point. Actually, yeah, maybe you can try to think. Give it to the students. Well, they won't solve it, but okay, amazing. Okay, but I will come to that in 2 slides. Let me first show the mod insulator. So, because that's now trivial, experts as you are, I start from small v. So now I'm deep in the mod phase, right? I've opened up a mod gap here. And so for v.4, I just have these 2 Hubbard bands. What happens now? Now I increase, and the peaks move closer, right? So you have, again, some effect that the effective U, and you could refer, for example, to the static value of that quantity, is reduced. So is the distance of the Hubbard bands. You have a second thing, and we'll come back to that. You are developing shoulders here. Anybody has a guess on that? There are satellites developing. Absolutely, yes. And I will argue later on that you will see that much more in detail. Just remember that I said the word here. This is kind of pseudo-plasmonic features. We are developing satellites from the screening, and I will go back to that in more detail later. Okay, but first, let me actually look at these screened interactions. And I really apologize. I found out that I don't have a figure for U, but only for the W local. However, if you believe me, then I tell you that the U of omega would look similar, just a little bit bigger, and also with this kind of characteristic frequency scale here. So we can discuss both on this plot. What do you see here? So this is the real part of the screen interaction, local projection. And here you see precisely the effect that depending on the value of V, you decrease, or if you increase the V, you decrease the screened part, the static part here. But of course, at high frequencies, you go back to the bare interaction. At high frequencies, epsilon goes to 1, so to say. There's no screening anymore. And you just go back to the bare interaction, which was something like 2.2 here. And you do that at some characteristic frequency scale. And if you look at that was the real part, at the imaginary part of that thing, at this thing, you have a strong peak. So that is a kind of, I call it plasmon excitation here, living at that energy scale here, but induced from screening processes which are purely non-local. Okay, so now let me look just at the static value of W, local part, and I plot this as a function of U for different values of V. Who can interpret this plot for me? Start in the large U regime. I take ideas. No, because you asked already the right question before. Okay, so in the large U regime, we are in the mod insulating phase, right? So there's not much screening, and so if there was no screening, you would be on this line, right? We are close to this line here. Then we go into the metal, and suddenly in the metal, screening is much better. So we decrease. And, well, then it was not that my student was too lazy to continue the calculations, but what happens here? And it happens the earlier more you have V, well, at some point, and that's the answer to Vijay's question, you go to the charge-ordered phase, and that means that actually your denominator in W diverges. So that means you cannot do the calculation in a single-side picture anymore. Remember, I told you, these are calculations doing all these self-consistency loops, but with really a single side, without any precaution of doubling the unit cell in order to describe charge-ordered phases. So what the method will do is just to blow up once you reach the boundary to the charge ordering. And that's what you see here. The curves stop at some point. Yes?
So the ratio of U by V is which you see the charge ordering. So it's roughly half, right?
Well, I mean, it depends somewhat on which regime you are in, because it depends on if you are in the metallic, deep metallic regime and so on. It's not just, you can just say, okay, it has to be this ratio. There are dynamic effects here. Yeah. Okay. So now, at least one figure about U, that's now easy to understand. This is the static value of U, so it's something like now the effective Hubbard U to be put in this local model. And again here, no screening in the insulating phase, and then you start to screen when you go metallic. Okay, so that's the thing. Actually, I was putting the plot, but I will not really comment the plot. I will just mention what we concluded from them. Namely, we were looking at the numbers for the non-local parts of the self-energy. And we were comparing that with the local parts and concluding that it was at least an order, if not more, of magnitude smaller. So that actually the non-local self-energy effects were really negligible here. That was not the main effect of the adding of the GW. My student was very disappointed in the first place, but okay, it's physics, and we finally understood, or we understood then, that it's not so unexpected because the GW will bring in charge fluctuations on top of the local physics, non-local charge fluctuations, but it will not bring in non-local spin fluctuations. And if you're in a 2D Hubbard model, that's probably the dominant source of non-local dynamical interactions. So that's the point I will come back to also. So that is certainly the thing which...
You mean by non-local, you treat the V as a GV, basically?
GW, but the W is screened in the charge channel only. Yeah. Yeah, exactly. Okay. So now, let me compare. Then he was of better mood again. Let me compare GW plus DMFT. That is the dashed curve here, with just pure eDMFT and GW. And here you see that, as expected, if the self-energies, the non-local self-energies are small, the eDMFT and the GW plus DMFT are not so different. Qualitatively, it's very similar. You have the Hubbard bands here, quasi-particle resonance. However, the GW, and here we did even a GW with the best G and the best W that we have, namely the converged GW plus DMFT ones, and you see it has nothing to do with the true spectral function. And that's, of course, because once you develop the Hubbard bands, you go out of the weakly correlated regime that GW is made for. You are out of the perturbative validity range. And that means you just screw up. And that's a question not of the starting point and which GW, which Green's function you take, but it's a question of the GW self-energy form. Yes? You mean this thing here? I think this is a question of the density of states, which is a little bit pathologic with this Van Hove singularity there. So it's a little bit separate. Yeah, yeah. But, okay. However, that does not mean that GW is not doing anything for you. So, first of all, it does not mean that it's not doing anything for you in general. I will show you that in realistic systems, this conclusion is largely altered. But I want also to show you that even if on the self-energy the effect is not so large, of course, what you have also the GW part in the polarization. And just plain EDMFT would give you, here what is plotted is the imaginary part of P, would just, of course, plot you something K independent, because you just add a local polarization. Now, what is GW plus DMFT doing is adding K dependence to that through the polarization of the non-local part, so the GG, and that gives a substantial modulation here in K-space. Let me interpret that a little bit more in detail, not on MP, but on a more physical quantity, namely what electronic structure people call, or not electronic structure people, the experimentalists call electron energy loss spectra, what can be really measured, and what is more or less given by the imaginary part of epsilon minus 1. So we plot that quantity now here as a function of K and omega. And what you see is that now the spectra differ quite a lot. In particular, if I focus on the GW plus DMFT thing here, it gets more sharp around the gamma point, has considerably less spectral weight around the pi point, probably because that is the K vector where we have nesting in this setup. And okay, in general, I should say these energies correspond to transitions between the Hubbard band and the quasi-particle peak, but they are modulated here now in K. And here at the pi0 point, we've developed two features, probably corresponding to the fact that we have in principle fluctuations in a stripe fashion where you would have correlations between the charge fluctuations on neighboring stripes of atoms. And that's what you can analyze here. So we can say something about the charge fluctuations developing in the system. I will come back to this point. Okay, let me skip this. And let me just give you a very short summary of what we have seen so far, just to put things in perspective. Very easy, 5 slides. This is what you actually know already. What are the different methods that we have analyzed until now? What do they do? So the usual DMFT was advocated to you as treating any strength of correlations. That's a nice thing, but cannot really deal with long-range interactions, but has a nice description of all that is local through this local self-energy, and by this mechanism captures the mod transition. Now, what we have extended somehow, we have, by putting the E here, we have extended things to non-local interactions. And we have seen that, okay, we have local polarization included here. The rest is more or less similar to what you had before. GW, completely different, handles local and non-local interactions, but does so at a perturbative level, and that is, it is confined to the weakly interacting regime. So that's what we saw on this kind of really, okay, I was told not to say vegetable spectral function, but the kind of boring spectral function here that GW gave you, which was quite far off. And the self-energy is just giving you some subset of diagrams to first order in W, even though it's local and non-local. Okay, and then, now you will not be surprised, GW plus DMFT borrows the advantages from both methods, so to say. It has the long-range interaction. So in the example I've shown you, just inter-set interactions, but we can extend that, and we will extend that in the next example. And then it has local and non-local polarization effects, screening the interactions, and you have seen the reduction of the effective view that you get. You have even seen that somehow now the effective view depends on the phase that you are looking at in the metal or in the insulator. It will be radically different. And you can argue that in terms of diagrams, you sum now at least the local stuff into infinite order. However, we also mentioned that one essential ingredient for low-dimensional systems certainly, namely magnetic fluctuations, are not included in a non-local fashion. Okay, so now you ask certainly, that was a nice model. I'm an ab-initio person. Can we do something for real systems? And as I warned you, this is a relatively new field. So this slide, I think, more or less summarizes everything that exists. And not even everything is GW plus DMFT, but quite a few things are LDA plus a frequency-dependent interaction plus DMFT, which I view in some sense as an approximation to that. So when we started actually in the initial paper proposing the method, we did something really bold and, well, simple. We just did LDA plus DMFT for the local part and combined with the non-local part for GW. That, from the perspective nowadays, you would barely call any more GW plus DMFT. Okay, then, as I said, what developed was a kind of method where you would do LDA plus DMFT, but use screen interactions in the sense of what Ferdi has shown you from CRPA. And there are a few applications now, in particular to strontium monadate, which is a constant somehow through this list, and also some more interesting material, barium 122, which we calculated with this frequency-dependent interactions. Then let's say the first real GW calculation, where frequency dependence of U was introduced, even though things were not self-consistent at the GW level, but at least self-consistent at the DMFT level. That was actually just this work 2 years ago on strontium monadate. And I will show you parts of that in the last part of my talk. Now I want to switch to this example here, because it connects directly to what we have seen for the extended Hubbard model and makes this somehow realistic. I will show you that this greatly simplifies our life. And then I also want to mention the nice works here, also on strontium monadate. So it's really nice to have different schemes tested on strontium monadate, because you can really see where effects are coming from, even though strontium monadate is probably not the material we want to stick with until 2020. So that is a calculation here by Taranto et al., who tried to just calculate a band structure from GW, quasi-particleize it, and then just do DMFT of it. Just instead of doing LDA plus DMFT, putting U on LDA band structures, just do it on GW. And then you can see actually that, okay, this has an obvious subtlety, namely that you count twice the local part of the GW self-energy, and that prevents you, in fact, from putting a dynamical U. Okay, for whoever's interested, we can discuss that more offline. And finally, then there's very nice work here by Sakuma et al., also with the help of Philip on the CTQMC, where actually they did a kind of one-shot GW plus DMFT in the sense that they used for the local part, in fact, the LDA plus U of omega plus DMFT self-energy, and then combined with a local part. So that's similar in spirit to this one, but here with the dynamical U. And as I said, if you compare, you can now really figure out where the effects are coming from. Yes?
The last one, or the first one, when you're double counting as a
Okay, so this work did not even care about the double counting, because they looked at the T2G manifold only. I will discuss what one can say and what one can't say here, because we spent some time on this. Yeah. Oh, I will tell you all the drawbacks and yes. Okay, but first I want to motivate you to listen further, so I want to show you an example that really nicely works. And that is the example of you take a silicon block and you put add atoms. And that can really be done. So our experimental colleagues did it, for example, here with tin. You can also do it with carbon, with lead, even though with lead the structural characterization is a little bit more difficult. And then this is a monolayer of add atoms here that forms actually a triangular lattice. So if you look at the system now from the top, that is what it looks like. You have the silicon 111 surface here and these thick fat atoms here. These are the, let's say, tin add atoms. They form a triangular lattice, and you can try to study that. Okay, let's study that, starting ab initio. We do, to get a first idea of the system, just an LDA band structure. And I show you this to argue that then we decide on a specific setup for our GW+DMFT, which is very special in this case. So the LDA band structure looks like this. So here we have plotted it for different kinds of add atoms, just as a function of k around the Fermi level here. And what you realize is that, well, you have silicon bands here forming a gap. Well, you know, that's silicon. But you have an additional band, and that is created by this surface state here, by the add atoms. These add atoms form a single band, so to say, which is well separated from the rest. So now you look at the bandwidth of this thing. So the energy here is 1 eV. So that's really small bandwidth. So you get immediately suspicious. Any interaction will make a single orbital model with this small bandwidth insulating. So we should have an idea of what is U. And here I'm not yet talking about GW+DMFT. I'm just talking about LDA. And now we look what would be the U in a Hubbard model constructed for the low energy subspace having just this band here. Yes?
What is the pink line and the black line?
Okay, what we did is we did the LDA calculation, and then we also did a tight binding parameterization of that, and then we compared. That was just for technical reasons.
So this band is from the p-set orbital of
Well, yeah, that's precisely the interesting thing. So it's a kind of carrot-like object, but it's not purely PZ. So it's a kind of, okay, I don't have a picture in this presentation, but I do have one I can show you. So it's a little bit more subtle because it lives actually on a relatively extended space. It's like a carrot, but it has kind of lobes in the 3 directions, and it's more interesting than just PZ. Okay, so the question is now, can we construct a Hubbard model for these add atoms with this single band and the U that we need for this? And what's the U we need for that? Well, you know how to calculate that. You do CRPA. And actually I have a reminder here. So in this case, very simply, you have your band structure. You have all the transitions that you sum up in a polarization calculation if you do it based on the non-interacting LDA band structure. And what you have to do is to cut out those that live in the low energy subspace, which is just simply this single band here. So everything which is here labeled as rest transitions from the silicon bands here to silicon bands here, transitions between the surface band here, silicon here, and silicon surface, that is included. And these processes, the red processes here, are the rest processes that you use in the CRPA to screen the interaction. And then you get, according to Ferdi's prescription, the U that you should put in the description of the low energy subspace here as the bare interaction within that subspace. Okay, and that is what was done here. And, well, remember your bandwidth, T, T prime, T double prime of the order of a few milli-electron volt here. The Hubbard U is in electron volt. So you conclude that you will immediately kill any metallic character. You should make it Maury insulating, if this is true. 1 eV, 1.4 eV, 0.9 eV. However, you can have second thoughts because precisely of the because of the remark that Vijay made. What does the orbital look like? It looks relatively extended, and maybe one should care now about not only on-site interactions, but inter-site interactions. So let's calculate the nearest neighbor interaction. I will show you. Yes, they are. to first approximation. So afterwards you can discuss different phases and if it's really doing that reconstruction, but to first approximation, yes, they are. I will show you data even. So now, let's look at the nearest neighbor interaction in EV, 0.5, 0.5, 0.5. So that's 50% of the on-site interaction. So, yes? Yes. So here the variation, excellent remark, is much less than here. And actually, you can rationalize this number even. Oh, I think I didn't get this slide. No, that was stupid. But I can tell you the rationalization. So actually, what you can do is a very dumb calculation. So we worked hard. We did this with CRPA. We took the non-local matrix element of this WR and so on. But then we were thinking in the following way. Let's assume you have the silicon surface with a certain dielectric constant. You know it, silicon. And you also know how to deal with screening on surfaces. You have some epsilon plus 1 over 2, whatever. So you know what would be somehow in a pure continuum description screening on a silicon surface. So let's check. We did that back of the envelope calculation, and we found that the nearest neighbor interaction is to the second digit, to the one I even didn't plot here, equal to the interaction that you get if you just take the bare interaction and screen it by that silicon surface continuum dielectric constant. No local field effects, no complication whatsoever. It's just a dumb dielectric effect. So that means you are somehow, for this distance, already in a continuum description. It also means the next nearest neighbor will be screened by that same epsilon, just with the corresponding distance. So you can very simply actually extrapolate what you will get, and you will get a Coulomb tail 1 over r renormalized by some epsilon. And the u1 is then actually essentially telling you that epsilon. So we can parameterize the nth nearest neighbor interaction by saying that it's some number, namely this 0.5, divided by the distance. So we have a full long-range Coulomb tail here, and not at all a Hubbard model. And that's logical. We are sitting on a semiconductor surface. There's no metallic screening. Okay. Okay, this is just for comparison, the bare interactions. If you had no screening, then you would get these numbers. And then you can check that if you didn't make an error, you take these numbers and put your epsilon for silicon. Okay, so that means what we should be dealing with is not an extended Hubbard model with the nearest neighbor interaction, but should be something which really has a long-range Coulomb tail. So I'm getting more realistic now, even though I stick to the low energy subspace for the moment. So I'm just considering everything in that restricted subspace referring to that one band. But I have now a model describing that band with ab-initio hopping parameters and long-range Coulomb interactions. And I can ask the question, can we solve that model now with GW plus DMFT within that confined subspace? And as you have seen before, for these one orbital models, we can do the full loop with all kinds of self-consistencies here. So that's really a full GW plus DMFT calculation confined to that space. And the results are quite interesting. So again, if you look as a function of local interaction, non-local interaction at the phase diagram, you find the mod insulating phase with, so the thing is half filled. Sorry, I forgot to say that. The electronic structure gives you that there is, on average, 1 electron per atom site. So that means you're nicely in the phase here where you have just 1 electron localized on each of the atom, and that's it. If U is large enough, that's it. If you decrease U, you get to the metal. If you increase V, you get into charge ordering. And charge ordering here is actually interesting. You triple the unit cell. You're on a triangular lattice. You triple the unit cell, and you have one side with 2 electrons, one singly occupied and one empty. Okay, so now, if we look at our compounds, the carbon one, which has the largest U, 1.4 eV, is deep in the mod phase. The intersite interaction was the same for all, but the onsite was smaller for silicon, tin, lead. So we move closer to here, and in our calculations for the lead, we even find that it's so close to some kind of phase transition here that we can stabilize two phases. We have a coexistence for that thing, where we get a metallic phase and a Monte insulating phase. And we didn't even look for the charge ordered phase. Okay, so now, are we doing anything related to the experiment? Well, the answer is probably yes. So that is unpublished data, so don't spread it. It's from our colleague Antonio Tejeda, who measured photoemission at the synchrotron, the spectral function here for tin on silicon. And our theoretical prediction is that you should have somehow these two peaks, and it's not so bad. So we are quite confident that we are doing something which has something to do with what happens really in nature. The two humps correspond to, oops, oh, now I should not make an error. I think the second one corresponds to the silicon band that comes in here. And the other thing is the Hubbard band from the tin. But I should say I forgot and could go back because we, okay. Let me not make a statement here because this is quite fresh here. And we were a little bit going back and forth. Yes?
So the bulk is actually insulating.
Yeah, of course. The bulk is the silicon just...
Yeah, and there is a phase in which the surface is metallic, and the lead is very close to that metallic.
Yes, yeah, exactly.
The lead will have some additional surface plasmons of some kind.
Yes, well, okay. So I showed you the thing for tin, because that is a clear-cut case. For lead, this thing exists as monolayer, but the surface reconstructions are not quite clear. So to my understanding, it depends a little bit how people prepare things, and then it's hard to measure. There are fluctuations, and this might actually be due to the fact that we are very close to these instabilities, that the thing actually wants to reconstruct in another way. Yeah. Okay, and actually, let's look a little bit more at this, what it wants to do. And for that, let's directly look at the charge correlation function. And let me now look at the charge correlation function for finite k's. So this is here plotted for different k, in particular around the m point and the k point. Let me tell you that, okay, so this charge correlation function would indicate your tendencies to charge fluctuations with a specific wave vector. That means announcing some kind of charge ordering, right? And if I look at what these wave vectors correspond to at the m point and at the k point, that corresponds precisely to this ordering pattern with 2, 1, 0, whereas at the m point, that corresponds to a stripe order that you could also develop. So going back, we can analyze now, and this is here for the different compounds, but you see that the question is really relevant, as you say, for the lead compound, where we have these two solutions, the insulating and the metallic one, and we see that indeed they develop some kind of maximum towards the k point, indicating that somehow there is charge fluctuation in that direction going on probably. Yes? This one? Yes. So we are really in a coexistence regime in the calculation. Okay. So the lead is really somehow, and that's why we didn't draw these lines through, is somehow where it's so close that, well, in the calculation we're in the coexistence. Okay, but now let me come back to U. And now let's really plot U of omega for the different compounds. For carbon, which has a large on-site U, 1.4 eV, and the intersite U was then just 1/3, okay, nothing really happens. You stay deep in the Monte insulator, you don't screen much. For silicon, you develop some kind of wiggle here. For tin, the situation is really nice. You have this developed kind of Plasmon resonance. And you see that the screened value, the effective local U in your impurity model, is kind of reduced compared to the bare interaction that you recover at large frequencies. However, for the lead compound, we had these two solutions. So we have two U's. And they are different. So in the insulating phase, we have this variation here. And in the metallic phase, we have a much stronger screening, very pronounced reduction of U, and very pronounced development of this Plasmon resonance. So that tells you, again, that the effective local U that will reproduce your physics here can even depend on the phase. Okay, so that is just a summary. That were all the parameters that we calculated. And now we added here this last line where we put the effective local U that GW plus DMFT wants to have. And that can not only be more or less half of the bare interaction here, but also different for the different phases. And also in particular, it depends strongly on the compound here. Okay, so now that was an example where we went to a realistic case, but in the admittedly very simple case where we just could confine everything to one orbital. What I want to do in the following is first to come back to some more general considerations. I have not said anything about dynamical impurities models really, so you don't know what is really the physics of that. So I want to catch up with that thing. And then I will show what is going on in the multi-orbital case, what we know, what we don't know, and where we are going. But okay, so first let's get back to dynamical impurity models. You have understood that the solution of an effective atom with a frequency dependence U and coupled to some self-consistent path is really at the heart of this GW plus DMFT description. So we need to understand what is the physics of this model. And I will not do that. And also we have to discuss how to solve that. We need to be able to calculate these quantities. I will not say much about this because Philip will cover it in the Monte Carlo lecture. However, I will cover it insofar as I think it's useful to understand physical insights here. And I will not do that in the most general case. There is, in the context of the Hubbard-Holstein model for phonons, a whole literature. I will just consider the limits that we are most interested in, and I think which are most instructive here, which is essentially the anti-adiabatic limit when the screening frequencies are relatively large. Okay, well, these are the three words I want to say in general about methods of solution. So there is very nice Quantum Monte Carlo nowadays that Philip will explain to you and that you can look up in this reference by Philip and Andy. Then we developed an approximate method, which is precisely nice in the anti-adiabatic limit and very cheap because essentially it allows you to do calculations with dynamical U at the cost of calculations with static U. And I will show you the general idea how that works. And finally, this is not really a method of solution, but I just mention it. You can also ask the question, can I, at least if I'm only interested in low energy quantities, can I map a dynamical model back on a static model? And the answer is yes, but you have to renormalize the parameters of the static model. And in particular, you have to not only use the screened value of U, but you also have to renormalize your band structure to take care of renormalization effects in the polaronic sense that I will show you afterwards. And that was worked out here in this paper with Michele Casula. Okay. But let me start with a question. So here, I have put up a dynamical impurity model. And actually, I realized I even put it up in a multi-orbital context, so the M's here are orbitals. Let's forget about that for the moment. Just don't look at the M's. You have here the part with the Weiss field, a dynamical propagator describing one particle hopping. And you have here the interaction part with some frequency-dependent interaction. The question you can ask, is there a Hamiltonian formulation to that problem? Let's take a poll. Who thinks yes? Who thinks no? Who thinks yes? Ah, it's not fluctuating in time. Why are you saying no, Thomas? Yeah? Yeah? Okay, I'm looking at the impurity model here. Okay, I convinced one customer. Good. Oof, otherwise I would have sweated now. Okay, so let's ask a question in a slightly simpler way. Let's assume there was no frequency dependence here. Is there a Hamiltonian formulation? Yes, you have learned that, right? Because then we're back to usual DMFT. That's the impurity model described in the action formulation. And you know that you can parameterize this thing by coupling your impurity atom to a bath. And this bath is parameterized by some degrees of freedom, actually infinitely many degrees of freedom if you want to have a real representation, that are equivalent to giving this. So you have studied, even on the blackboard, how to write this in terms of these epsilon and v, where the epsilons are the levels of the bath degrees of freedom, and the v are the hybridizations, are the hoppings between the impurity atom and these bath degrees of freedom. Yeah, I'm getting there. So in the case there was no frequency dependence, this would just be the representation. And so now Vijay wants to have a bosonic bath, and I was doing that slowly because I thought you had not seen that, but maybe you have. So indeed, you can do an analogous thing with the frequency dependence of u. You need to introduce additional degrees of freedom. They are bosonic, and if you write a bosonic Hamiltonian, here B dagger B, creating annihilating a boson with frequency omega nu, and these bosons coupled to the fermionic density here in this way, then you find, and okay, your interaction part now has only the unscreened interaction. This would be your bare interaction, the bare V or whatever you had in your system. Then you find that if you take that Hamiltonian on top of the part with the Weiss field, and you integrate out the bosonic degrees of freedom, you get back to a purely fermionic model with frequency-dependent interactions. And that's natural because you know probably or maybe that indeed Hubbard-Holstein model can be mapped then on a Hubbard model with dynamical interactions. So how does this U look like? Okay, let me take the case with just... So the blue line is kind of reminiscent of what you had before. This kind of Plasmon pole given by the characteristic frequency here that we have seen in our models. So for this reason, when we have these resonances in the U of omega, I will talk about a boson that lives there. I will even call it Plasmon. The dominant divergences that you get in the CRPA, for example, for Strontium vanadate, you have seen the thing at 15 eV, are the Plasmon precisely. I will also use the term Plasmon a little bit abusively because all the features in this bosonic spectral function I will call Plasmon, even though, of course, there's also particle-hole excitations and everything living in that space that is screening that I will just call with that. Okay, so now the question, what does a Hubbard-Holstein model do if I put a boson and if this boson has a large frequency? So if this energy scale here is larger than all the other energy scales of your problem, whatever, bandwidths, crystal fields, whatever you may have. Well, let me give you a calculation which looks like a caricature. So that is for carefully chosen parameters, namely for a plasma frequency of 10 in some units, which is probably half bandwidth, which is much larger than the infinite frequency U and the zero frequency U. So these two numbers essentially are related to the coupling strength, the lambda that you had. And this tells you that the biggest energy scale is indeed just the Plasmon. And what happens in that limit is that, well, you get this spiky stuff here. Who can interpret this for me? No, you're not eligible. Anybody else? Okay, there's a quasi-particle peak, yes? Hubbard bands, exactly. So we are first starting with everything here which lives on the Fermi level, right? So quasi-particle resonance and Hubbard peaks. So that is the familiar three-peak structure that you are used to. We just plotted everything on a very large energy scale because we wanted to see also these additional features, and these are the new ones. Everything that lives here is what you have seen before. And what are these new ones? Plasmon replica. So what happens? You do a photoemission experiment, right? To measure this thing, you need to extract or to add an electron, right? And the spectral function is essentially telling you at which energies you can do that. So now what happens is, with the new model with these bosons, you can do everything you could do in the fermionic model. Add, remove an electron. So here for the negative frequency part, remove an electron, take it out. For the positive frequency part, add an electron, and you will have the quasi-particle peak and the Hubbard bands corresponding to these processes. But you have many more options now, because you can do a process where you add or remove an electron and at the same time create or destroy a certain number of bosons. One boson has an energy of 10 in these units. So if I add or remove an electron and at the same time create or remove a boson, then I will just replicate this structure at the shifted energy where I add plus or minus a multiple of omega 0. And surely, if I go to many bosons, the probability will become small, but you will have an infinite tail here of possibilities of adding or removing bosons, which kind of are little caricatures of the corresponding part of the spectral function. Yes?
It seems like you're taking this three-piece structure, slice it,
Absolutely. Yeah.
so that three-peak is securely occupied.
Exactly. That's exactly the thing. You take the thing, slice it, and propagate to the respective sites. So now, that's nice. Physically, we understand this thing.
And can we say anything about the relative intensity?
Exactly. So now Tanushree is heading 2 steps ahead, but that's the direction I wanted to go anyhow, because what she's saying is, well, this thing here looks like the familiar three-peak structure, but it will not be equal anymore to what you would calculate without the dynamical U. Why? And now Tanushree doesn't answer, please. Why is this, even though it looks very familiar, not exactly the same thing as before? Can't be. Spectral functions are normalized. So if you integrate everything here, adding, removing an electron, this thing is normalized, okay, in this case to 1. And this will not change because you have more possibilities with plasmons to create or whatever. So the whole thing is normalized. If you integrate everything here, it's 1. Before, you were looking in a low energy window and you were getting a three-peak structure, and that was normalized to 1. So that means everything works as before, except that you lost spectral weight. So you have, again, this three-peak structure, but it will have reduced weight, and the weight is actually going to this replica. And the answer is yes. So I will not show this, but this is the reference of Kazula et al. Of 2012, PRL 2012 that I showed. You can work out analytically what is the weight, and that is the way also that you could then put up to directly do calculations just to look at that without really doing the frequency-dependent U. So if you decide that you are only interested in that energy range, in that subspace, I'm talking too long on one slide, then you can actually just do that estimate and renormalize things by that. Okay, anti-adiabatic limit means that this frequency is the largest energy scale. And that's what I used here, because otherwise, if things come closer, you entangle structures of the Hubbard bands, the replica, and things are not as simple anymore. So there's a whole general literature on Hubbard-Holstein models in all different limits, in particular the phonon limit, which is usually the opposite one. However, I will stick to the one that I will use here. So that's why I just took the adiabatic one.
So the spectral weight transfer is proportional to the coupling constant square.
It is like exponential of minus lambda squared over omega 0 squared. Yeah. Exactly. It's exactly a Polaron effect. So you can strictly show that you do a Lang-First transformation, you project on a zero boson state, and that is the Lang-First weight. And okay, so for people interested in, I thought about including it here, but then I dropped it, but you can really look it up here. So that gives you then this mapping on an effective static impurity model where you would just calculate that low energy weight. And that's what I alluded to as saying this is electronic polarons, because it's an effect where the mass of the electron gets heavier through the coupling to these bosonic degrees of freedom. It's not polarons in the sense that you couple an electron to a phonon, but you couple an electron to these density fluctuation Plasmon things, and that's what makes your electron heavier, and that's why we say polaric effects. Okay, let me understand this kind of picture yet in another way. And to prepare that, I want to discuss a nice limit, which I call, yeah, oh, no, there's a question.
What happens if you add more modes to the bosonic?
Okay, if I have more bosonic degrees of freedom, yes. Nothing very special. The thing that you would guess, namely, that you generate additional replica corresponding to these possibilities. And you can even have a kind of continuum of bosonic densities of modes, and then things look a little bit more complicated, but it's still the same mechanisms. Yeah, very good question. How what?
So I just have a single mode, but if I increase U,
Yeah.
then I would develop, instead of having a quasi-particle peak at omega equal to 0, I'll develop fully.
Okay, so if you increase U, but still stay in the antiabatic limit, then you would just have Hubbard bands here and replicate those. However, if you increase U such that you're out of the antiabatic limit, then things will get entangled. Okay, so now let me go to a very nice limit that we can solve exactly. So the impurity model in the dynamic atomic limit. What do I mean by that? Well, what I mean by that is that we take an atom which still keeps its dynamical interaction, but doesn't have any coupling to a fermionic bath anymore. So I guess yesterday, or I think yesterday, you studied, for example, in the IPT context also, the usual atomic limit, right? So you were saying you put the delta, the bath hybridization to 0, and then you get a very simple description of an atom, and you have the atomic levels and so on. I do the same thing here, except that I keep the frequency-dependent interaction. So no fermionic path, but U of omega remains. Then the question is a little bit less trivial. It takes a little bit of work to work it out. But you can solve that thing analytically. And the answer is given here and is really interesting. So what happens is that, oh, sorry, forget about the M again. That was for orbitals here. What happens is that the Green's function for that case factorizes. So it factorizes into something which is exactly the atomic limit Green's function that you studied yesterday for a case with static interactions chosen as being the static limit of U, the U of 0, so to say. You look at your function U of omega, take the limit omega to 0. That's the static U, what I will call static U. And you calculate the Green's function for the atomic limit with that static U interaction. And that's the first factor. So now, the omega dependence of U enters in Fourier components that I call UN here. And all the non-zero Fourier components, the ones other than the static ones, they enter into a second factor which looks like that. So I wrote things in tau space here, and then I wrote factorization in frequency space. This morning I reviewed my slides, and first I thought I made a misprint, but no, that's what I meant, because it means that this thing depends only on the zero frequency component of U, and this factor depends actually only on the finite frequency components of U. And that's an exact property in the atomic limit. You can work this out then how it looks in practice, so actually you know it because you have calculated that yesterday, and that's the thing you get. So now you can think that what would happen if we just keep this kind of factorization even away from the atomic limit. And that's what we actually did when putting up these Bose factor ansatz. We were assuming that we can, even for finite path, write an ansatz where the Green's function factorizes into a Green's function of a static impurity model with static u equal to the zero frequency limit times some bosonic factor encoding the finite frequency contributions of u. And then you can ask, where do you get this factor from? In principle, this is a general ansatz just to factorize things like this. But you can ask, what happens if you just take this from the atomic limit? If you take this from the atomic limit, then this thing actually looks like this, and this is what we call the dynamic atomic limit approximation, or DALA, nice name. Huh? So that means we write the Green's function, that's an exact rewriting, as the Green's function divided by the Green's function of a static impurity model times this thing, and approximate this first factor here, this thing, which is then exactly this b, by its value in the atomic limit, which is nothing else than saying that we take the exponential of the slide before. So approximate g by taking the exponential of the slide before, encoding all the information about the finite frequency components of u, and you have to solve your impurity model only for the zero frequency u. We benchmarked that against direct Monte Carlo, and we found that in the anti-adiabatic limit, in the limit where really this omega 0 is large, this is an excellent approximation. So we are really happy to see that. Furthermore, it has a consequence, because if we have a product for the Green's function in tau space, if we go to Fourier space, we get a convolution. So the analytic continuation is not only greatly simplified, but gives you also some physical insight, and that's why I insist on this. Namely, you can write the spectral function, remember, imaginary part of g of omega, essentially. You can write this as a convolution, essentially, of the spectral function corresponding to the purely static impurity model with the spectral function corresponding to this bosonic factor. And some dressing here because of finite temperatures.
So basically, that is, you have the same spectral function copied at different
Exactly.
and then these are the rates.
Exactly. So what you do is, this is a thing. Let's assume I'm in the one-mode Hubbard-Holstein model for simplicity. Then this is just a spiky thing deciding that omega 0 is pinned here, some kind of delta peak. So now I convolute this thing, the spectral function of the low energy static Anderson model, Anderson impurity model. I convolute that with a spiky thing, so that means I replicate this thing with the bosonic part, which is determining me the positions of where I put my plasmons. So that gives, to my taste, a very nice kind of mathematical understanding why you indeed generate just this series of peaks there. And as a side effect, it also allows you to do calculations just at the price of calculations for a static impurity model and have a much more well-behaved maximum entropy analytic continuation for that one. If you were directly trying to continue this one, you would have probably you will have large troubles because you are searching for spectral weight at very high energies, which is very hard. So that's a nice side product here. Okay, so we understand this. And let me just summarize a little bit what we have understood now about the effects of the dynamical U here in our impurity model. We have seen that we get this Plasmon replica at the characteristic energy scales given by the bosons. This corresponds to spectral weight reduction that I told you can also quantify, even if we will not use it today. And the static component is reduced. Actually, it's reduced from its infinite frequency value by, here I wrote you the thing for a multi-mode Hubbard-Holstein model with the couplings of the different mode divided by the energies here. You can also view this thing here actually as the imaginary part of u of omega if you have a continuous distribution of frequencies given by the imaginary part of this function. Okay, so now let me ask a question. We have talked about dynamical screening, frequency-dependent interactions. And actually, a few days ago, we had an analogous lecture. You were talking about frequency-dependent interactions, dynamical screening. Ferdi showed you figures like this. What's the relation? Is it the same thing? Is it completely unrelated, or is there some link to make here? What are the physical mechanisms? Excuse me, I'm just 10 minutes before end? Oh, okay. I should hurry up a little bit. So, please hurry up a little bit, tell me the physical mechanism. So in Ferdi's case, or in the CRPA case, you were starting with a band structure living on high energy scales, and you were asking the question, can I downfold to a low energy space? Can I find an effective interaction, which is the bare interaction within that low energy space, and which is screened by everything else that I don't include anymore, right? So here, actually you may not have realized, but to some extent, I'm doing something similar. Namely, I'm asking the question, here, I want to describe my full physics, local and non-local, within a local model. In that local model, I only have the P impurity left to screen. So I want to reproduce W impurity from some effective bare interaction to be put in this local model by screening it only by this thing. That's analogous to that equation where you said, okay, I want to have the W, and I want to have that from some effective U, which is screened only by low energy degrees of freedom. It's just the question of which degrees of freedom we cut out. So to some extent, the CRPA equation here, so here I'm just rewriting what you wrote as U is the bare interaction screened by the rest, and then you take it, screen it further, and you come to W. So that's just another way of rewriting the CRPA equation. It's nothing else than doing a kind of, well, I wouldn't call it CRPA anymore, but we call it constraint screening approach on the local versus non-local separation. And that's really a general feature. When you restrict your Hilbert space to some smaller sub-Hilbert space, you eliminate some degrees of freedom, and these degrees of freedom have to renormalize your effective, bare, whatever interactions in the space that you still want to treat. In the one case, it was downfolding in energy space. On the other hand side, it was now downfolding or backfolding of non-local degrees of freedom into something effective local. So there is a relation, and this relation is even interesting because now you can think of the following. The full GW plus DMFT prescription, as I've shown it to you, is in principle telling you that you should treat all orbitals on the same footing, right? We were saying the separation is local and non-local. I'm not talking about correlated subspaces, uncorrelated states, whatever. However, this comparison with the CRPA teaches me that maybe I can get away somewhat cheaper. Asking the question the other way around, you can ask, shall I really solve an impurity model for oxygen p states? Or maybe I should think in a way that I do a downfolding of CRPA type and then solve the remaining thing within the local plus non-local distinction. That means with a true GW plus DMFT. So conceptually that is appealing, and well, since we are lazy people, it also makes our life easier. So we don't need to treat ligand states here or empty conduction band states in impurity models, which would be horribly large, but we treat those in the example that I will show you now, just on the level of the GW approximation, and do DMFT for correlated states only. And that means that you actually are deviating somewhat from the general scheme that I told you, namely that you're not replacing the GW self-energy, the local part of the GW self-energy by the impurity model, but you're replacing only the D part, let's say D for correlated here, because most of the time it's the D in transition metal oxides. So what I note here is the correlated subspace that I chose now. I replace just the D part of the local GW self-energy by a self-energy for the D space calculated in DMFT. So that equation has some kind of double downfolding plus backfolding. Same thing in principle for this P part, even though I should add immediately that in this reference that I gave you, we did something even more bold. We just took the U of omega from CRPA in the way Ferdi calculated it, and then we did GW plus DMFT in the way of the orbital separated scheme that I had just shown you by doing DMFT and the T2Gs and keeping everything else on the GW level. And now I should make a choice of which slide to show you. So I'm 3 minutes from the end, and I probably just show you the very last comparison, and then we keep time for questions. Okay, well, let me do it even. Okay, I have to come back to finish the lecture in 2 years, right? But this is the result that you get then for this, your favorite compound Strontium vanadate. And for those of you who attended the conference, you probably remember this slide. So what you see here is that you have the ligand states, oxygen, and the empty conduction band states. You have the T2G manifold somewhere here. You have an additional peak, which before was identified as an upper Hubbard band in the DMFT, but which now we attribute to EG states. And our main conclusions are that the GW plus DMFT, thanks to the fact that we do DMFT within the T2G subspace, generates nicely the lower Hubbard band here, has a nice description of the T2G, but doesn't have an upper Hubbard band, but instead places the EGs at the experimental photoemission position. Okay, then there's a second question, and that is the question of where are the uncorrelated states related to Andy Miller's lecture and to what we said before. Should we really start from DFT concern bands? That's the question I asked on the very first slide. Well, you see part of the answer here. The empty conduction band states are nicely agreeing with experiments. I should have shown you the LDA nevertheless, which was not the case before. Oops. So before, the LDA had them considerably too low. For the oxygen states here, LDA had them way too high. What we find now is that the oxygen states are indeed corrected somewhat, but not the whole way. And the strontium D states are very nicely at the right position. Okay, so that's this thing. With this, let me jump to my conclusion so that I still have 2 minutes for that. So let me finish by reviewing what I think you should expect from GW plus DMFT and also what you shouldn't. So let me go through this. We said, okay, the whole business was in order to make GW fit for strong correlations. I think this is a fair statement, and we have enough data to say that indeed that's happening. The T2G manifold develops a Hubbard band at the right position, and so on. Also, we were making a whole discussion that we want to avoid the mismatch between the long-range Coulomb interaction and some Hubbard parameter chosen in some way. And this became possible because now this U in principle has become a self-consistent quantity. So we don't have a U parameter anymore, at least if we do everything self-consistently as in the concept. Description of uncorrelated states is beyond DFT. In how far we entirely reach the correct position has still to be looked at. So in the example that I've shown you, For the unoccupied states, we were very happy. For the ligand states, we were half happy. However, as I said, that was not self-consistent at the GW level yet. There's questions of how to link P and D states, sigma PD. So I think there is still room for improvements, even conceptually. So this is why I say, okay, I would expect that the uncorrelated states should come out in that scheme, but we don't have the complete proof yet. Conceptually, we got rid of double counting, even though I should add, again, you should take care if you make separations in orbital space. This is not justified by a functional, so you should make some thoughts of how to treat the inter-shell interactions between a correlated and an uncorrelated shell. And finally, I think this we can say, based on the model level results, the issue of self-consistency of GW, or the issue of not being able to do self-consistency in GW, I think is cured by the presence in GW plus DMFT of a local vertex. So when you do GW, truncate the perturbation series after the first order and iterate, Ferdi has shown you that the spectra screw up. If you do GW plus DMFT, you have the GW, but you have also a local vertex. If you iterate that, at least in the model level, it seems to be very nicely surviving. So that, I think, is the nice point. Now there's also some little weak points. So we have discussed that non-local spin fluctuations are not included, so you should not expect to solve the hotspots in cuprates with that. This is understandable because we are looking at screening in the charged channel only. We have charge fluctuations nicely, but we don't do anything about non-local spin fluctuations. And this is what we believe to be the reason that the self-energy effects, the truly dynamical self-energy effects in the model are small. However, that does not mean that in general non-local self-energy effects are small. Because in the strontium vanadate case that I didn't show you in detail anymore, we found that actually non-local self-energy effects beyond DFT-LDA are huge. It's just they are static. You have a correction to exchange which goes beyond the LDA and which is replaced by something like the screened exchange of GW. And that is a big effect, but that's an effect that you don't see in a simple Hubbard model, where we just look at half-fill. So don't conclude from this that non-local self-energies are not doing anything in general. I think the inverse is even true. And in real materials, I think this is one of the challenges to explore the exchange effects, actually, that enter here in the scheme by this thing. Finally, I think there is a second delicate point, but that has not yet completely worked out, namely to investigate the dispersions of two-particle excitations. I think there is some bias due to the fact that the polarization always keeps the local part and, for example, is not able to go to 0 for q equals 0 limits or things like this. So I think there's also some work to be done still on Plasmon dispersions. Okay, so I covered already large part of what I put now under the perspectives. It will be very interesting to push this further to look at full self-consistency, not only in the simple case of one orbital models, but really at a multi-orbital level, and to see what happens then in realistic system. In particular, as I said, with the uncorrelated states, do we push down the oxygen p states sufficiently if we calculate them in a GW that knows about the strong correlation in the T2G shell or not? You've also seen that, well, there's choices to do. We can do separation local, non-local only. We can do it orbital separated. We are at the moment, and I think that's a fair statement, very much still guided by the physics. We are not just putting atomic positions, pushing some buttons and looking at the results, but we are thinking, should I do DMFT on the T2Gs only? Should I do it on the full space? What should I do? And I think an interesting question is to really explore which of these different choices are reasonably equivalent and which ones are maybe also stupid. Okay, I discussed spin fluctuations beyond GW. I discussed Plasmon dispersions. What has not been looked at all is total energies within the scheme. And I think we need many more materials now so that our list is not only strontium vanadate. And eventually, but that was the thing that I was already advertising in the conference, that is a question also largely to experimentalists. It will be very interesting to look at the predictions that we have already for unoccupied states where things seem to be quite far from the LDA plus DMFT prescription. Okay, and with this, I put up a whole list of references, and then I realized you will never have time to write them down, and then I realized you don't have to, because essentially you go to the Psyche highlight published in June 2013, which is available on the Psyche webpage, and there essentially you have all these references and a little description around and so on. So just Google for that thing. Okay, and that's a slide I had already. If now you got curious and you understood that there's a lot of more things to work on, which are very challenging and interesting, then please don't hesitate to talk to me. Thank you very much for your attention. And just the last slide. So we are not only doing strontium vanadate, so these are examples of what we worked on in recent times. Thank you very much for your attention. Yes. Which one?
The strontium vanadate,
Yes.
for which, of course, you have done LDA plus DMFT, as well as GW plus DMFT. How much the computational effort goes in moving from one scheme to another scheme, just to give an idea.
Okay, so now it depends very much what you call computational scheme. So let me answer for the existing things. So let me answer on the specific example here, which I have half shown you. So that thing needs a GW calculation, of course, full space with all bands, whatever. We did that at the one-shot level only. So that's a serious calculation, but feasible, of course. So then we did the DMFT for the T2G space only, and we did it within the Bose factor approximation. So that means we do the calculation at the cost of a static impurity model. So it's a thing that you do in the tutorial this afternoon. The cost is not more heavy. What is tricky is then to do the analytic continuation. So there we use this convolution thing. Then you have to look, because you have the GW on the white scale. You need to be careful about chemical potential. So there is things where you do not just have an automatic code, but the computational cost as such was not very heavy for that thing. However, this is not saying that any GW plus DMFT is just cheap, because if now you go back and you want to update things, so I think there are probably people in the audience better placed than me to tell that GW calculations, if you want to do updates, you cannot use the simple polarization formula, for example, just looking at transitions. You need to really work with GG. There are a lot of subtleties related to the update of the GW and to the convergence with respect to the number of states and so on. So I think the bottleneck in GW plus DMFT for many years was certainly the dynamical impurity model. So in 2003, when we started this, we knew that we should solve a dynamical impurity model, but we had no means to do that. So we did it statically and added and removed and whatever. That's now under control. So Philip will show you the very nice Monte Carlo. I've shown you the things on the Bose factor approximation. There's even the paper that I cited by Li Wang, a Chinese guy who re-implemented the CTQMC and redid the calculation for strontium vanadate. And if you compare to the Bose factor approximation, Bose factor ansatz, it coincides. It's really great. So I think the impurity model with dynamic interaction is now under control. So now I think things move back. Now as we say in German, the black card is back in the camp of the GW community. How to make GW codes more efficient, more safe, also with self-consistency, and to work in that direction. And that's intimately related to these questions of multi-orbital, how to combine, and so on. Yes?
I'm not fully understood all the details, but there's something that's bothering me, which is the following. So you're working some truncated subspace of your full Hilbert space. And then you're finding some excitations there, like for example your Plasmon, which is 10 electron volts. And that sort of crosses the band gap of this into the other bands. So is there something? So you would have thought that everything is within.
No, because okay, it's an excellent question, and I think it's very hard to give a full answer. But I think my opinion is the following. This separation of subspaces, you can strictly not do it entirely. Because you do an excitation in that subspace, and you have screening from the other subspace. And that is precisely the reason why you don't have a strict functional formulation of the orbital separated scheme. So as long as you keep things to local and non-local, you can strictly separate. That's the non-local, that's the local part. As soon as I write T to G local and everything else from GW, you have the problem that this is not coming from the functional, and that's not just a mathematical thing, but it's precisely the physics that you're saying. Namely, you do a perturbation in the T to G space, and that has some consequence there. So I think on conceptual grounds, there's no solution to that problem in some sense. So there is no functional. However, that is kind of a fundamental question. I mean, if you do this kind of downfolding, you are limited by this physical aspect. So I don't know if the answer was very clear, but I think it's really a conceptual thing. And at some point, we have to make an approximation.
Yes, sure,
so now, for the position of oxygen ligand states, this effect will probably not play. So I think even if there's no functional, it's a reasonable thing to assume that non-T2G physics is given by GW kind of approaches. So I think the assumption behind that is to assume that the vertex is actually not playing a role if you are at sufficiently high energies. And that is certainly true, that you cannot so show. So you have to keep the vertex somehow in the low energy subspace and can neglect it in high energy one. But it's a neglecting, and it's no rigorous thing.
So if we neglect the plasmon, will that Hubbard bands and other things, quasi-particle and Hubbard bands, will that be reproduced? If we neglect that plasmon?
Yes? Okay, very good question. So you're asking about the comparison of, let's say, LDA plus DMFT static Q and dynamic Q.
Right.
Okay, that gives me occasion, thanks a lot, to go back to two slides that I would really have liked to show. Namely, the standard LDA plus DMFT calculation with some static Q, which gives you the Hubbard band here, quasi-particle peak, and then this thing which had been interpreted as Hubbard band, but where I said we take issue now. But let's not focus on this now. Let me look at this thing. So this is at energies which are, well, 1.8, nearly 2. And that has always been a problem, because experimentally this thing is more at 1.5 actually. So now, if you do the calculation with static interaction, so on this slide it's not very nicely visible, but you shift to lower energies, because your separation of this feature and this feature, so it's the green curve here, is now the static Hubbard Q, the effective one, which is smaller than the initial bare interaction. And it's smaller. So in this case, it's about 3.5, which gives you for the 1.5 here and the 2 here, because, well, in the initial calculations, people have adjusted the U such as to give you more or less the right quasi-particle weight. And if you don't have the polaronic renormalizations, then you need a larger U to have the quasi-particle weight more or less correctly. Here, what you see is that since you have this pre-renormalization by the polaronic features, you need a smaller static U to get the right mass renormalization, and that means the Hubbard band distance will be smaller. And that's why this Hubbard band moves up here. So there are subtle differences due to the fact that you have these polaronic features and these additional renormalizations.
But there is also some change in the quasi-particle
yes, so that is due to the fact that, okay, on the one hand, or actually that's the main effect, you shift the spectral weight.
Yeah.
So what you see here is precisely the effect that we discussed before. The red curve is normalized to 1, whereas the green curve is normalized to this kind of exponential of, which is the weight of the zero boson state. Absolutely.